So, what we have next is a rod has length 6L, okay, and mass M. Find its moment of inertia through an axis perpendicular to its length, through its midpoint, okay. Through its midpoint, guys, means this way here. Can anybody tell me the regular formula for that? It's a third, you get this from your notes, a third ml squared for a rod that's held from its center. Okay? So guys, go to page 53 and you find that when it's from its midpoint, page 53 of the tables, when it's from its midpoint, that's grand. However, this formula is set up for mass M and length 2L. We have a length of 6L. What does that mean we should do with our L value? Any idea what we should do with the L value? 3 times it. 6L is 3 times bigger than 2L. So we're going to 3 times our formula. It's going to be a third M 3L squared. And what we're going to get there is it's just going to be 3ml squared. Is that alright? Next formula we're doing is around about the this one is about its end, through one end. Okay, so we're talking about through one end. We're talking here, and we're talking that it's spinning like, oh dear, it's spinning around by the end. You get the picture. Okay, it's spinning around that way. Yes. Good. Yeah, it turns into a 9, doesn't it? Yeah, yeah. Okay. So this formula in your notes, your inertia of a rod when held at its end is 4/3 ml squared. That is a system of length 2L. We have a system of 6L, which means our length is 3 times bigger again. 4/3 m times 3L to be squared. And what do we get then? Anybody? We should get 12 ml squared. Actually, guys, just while I'm here, this is actually annoying me. There we go. Back to the way it was. Okay. Everybody cool with that? All right. Next one after that. Through a point which is L from one end. L from one end. How are you going to do that? Okay. So I just want to describe what we're basically going to be introducing is the parallel axis term. Now let me explain what we're doing here, right? So if I set up a system again, and I can do it 2 ways. I'm just going to show, actually I'll do it 2 ways because it'd be nice to know that you actually have a bit of choice here. Okay? So the one thing that they all have in common is, what do they all have in common? They're at an axis that's perpendicular to its length, going perpendicular to the length and spinning it around. All 3 axes are parallel. Would you agree with that? They're all parallel. Okay? So all 3 axes are parallel. From a top point of view, if I was to draw this, and this is like sort of coming out of the board, the 3 axes is that this one here is the axis at one end. That's the axis through the center. And the next one can be the axis that is a distance 1L from one end. All 3 of them are perpendicular. All 3 of them are perpendicular to the rod. 1, 2, 3. Okay? So, what we can do is we can do 2 things, okay? We can say that's its center. It's a distance L from the end. That makes it a distance 2L from its center. You happy enough with that? Since we know they're parallel, we write down the parallel axis term. Okay. We call IC its inertia from the center. What's its inertia from the center, guys? Inertia from the center. We had it earlier. IC is 3 ml squared. We won't call it L. We need another letter for that. I'll call it B, axis B. So IB equals IC plus MD squared. IB is equal to 3ml squared. I'm taking it from its centre. Okay. Now it wants is what is the mass of the object? Mass of the object is m, isn't it? So plus m. What is the distance from the axis I'm currently talking about, which is going into the board, compared to the axis that I was using, the central axis? What's the difference? 2l. Add them together, you get 3ml squared plus 4ml squared to give me 7ml squared. Everybody happy with that? I'm going to do it a separate way now. Okay? See the way I used it from the center that time? I could also have done this question using the end. So as an example, that's B. We'll call this axis E to say that it's from its end. What's the difference between the two axes? L. Inertia about B is the same as the inertia about E plus md squared. IB therefore is, what was the axis around its end again? 12ml squared. That's interesting. You have to do it from its center. So we a basic criteria. The axis going through the end is perpendicular to the rod, as is the axis through B. But yet when we combine them in the parallel axis theorem, we'll get an answer that isn't 7ml squared. Not even close, because the IE is 12ml squared. That is because the parallel axis theorem is derived from the center of gravity. Therefore, in order to use the parallel axis theorem, you must use a moment of inertia about its center of gravity and then make the adjustment outwards. Is that alright? Do you want to take a note of that? So when you're using the parallel axis theorem, the axis you use in conjunction with it is always the IC, going through the center of mass. Yes, Tom? But you could. Now, question 2. We have a lamina, okay, and this lamina here is need to make this a bit smaller. It's a rectangular lamina, length 2L, breadth L. Now, there's something very interesting about the lamina, okay? We learned this from the previous exercises, that it only depends on how wide it is around the axis. So, as an example, if I'm talking about this axis A, see axis A? Axis A has 2L going to the left and 2L going to the right. So its generic equation, like your inertia about axis A, should be a third ml squared. That is if the full length is 2L and the mass is m, that's the formula we use. But what's the full length this time? What's the full length this time? 4L. You only care about the axis A, and you only care about what's to the left of the axis A and what's to the right of the axis A. You don't care about up and down. You don't care about how far it goes down. That actually doesn't affect it whatsoever. It's only what's to the left and what's to the right that affects it. The distances left and right. Okay? Please hammer that in. Remember that now. Okay? So we're saying that our formula here works for a length of 2L. We have a length of 4L, so we got to scale that up a little bit. So just one sec. So IA equals 1/3. Is it still mass m? If that was mass 2m, I'd change it to 2m. And then 2L to be squared, and we get 4/3 ml squared is the moment of inertia about A when you're flipping the page around the axis. The axis is parallel to the sides. Okay? Axis A in the plane is the keyword. In the plane means it's parallel. Gary, you have a question? So, next one I'm doing is axis B. Axis B is here. It's going to the left. I'll do it in red if we can. Here we go. Axis B. Now, axis B, you're only concerned about up and down this time. You're not concerned about left and right. You're only concerned about the region above and below. How wide it is as opposed to how long it is. So you're only concerned about the height. It can go on longer and it will remain unaffected. But if I go down this way and up that way, its moment of inertia is affected. Okay? So, what we have here is IB. IB is a grand system because it's of length 2L. Its length matches the generic formula, doesn't it? So all we can say there is IB, is it, guys? So axis through B, the plane of the lamina. Sorry? No, it should be a third ml squared, and I should just put in. Is it at the end? Is it? Axis B. Sorry? Same as the pre-rehearsed one. Stop it for a sec. Okay, 2L. L. Oh yeah. Sorry guys. These solutions. In these solutions, they actually did a misprint. That's what's confused me. As in, they got their A and their L. They got A and B mixed up. So that's why I'm just looking at it down in complete confusement. Right? It's actually exactly like the regular formula. It's a third ml squared. Is that okay? Good with that? Alright. Now, they want the axis through both of them perpendicular to the plane of the lambda. So they want it perpendicular to the plane of the lamina. So originally, one of them's flipping this way, the other one's flipping this way, but between the two of them, there's a perpendicular one that's going to cause it to do that. Does everybody agree? Perpendicular one. So guys, there's a perpendicular axis going through this point here, and it's going into the board, causing it to rotate around this axis. It's perpendicular to IA and IB. So we're going to do the perpendicular axis theorem, and we're going to say is that we'll call it IC. IC equals IA plus IB, and what you're going to get is a third, what did I say, forward 3 ml squared plus a third ml squared gives me 5/3 ml squared. Is that okay? 5/3 ml squared. Brilliant. Okay. Once we're done with this next, excuse me guys, focus on the board, yes? Okay. The axis through P perpendicular to the plane of the lamina, but it has to go through P this time. Okay? So we're targeting this axis here. Just coloured in a red dot. And what's going to be happening this time is that it's going to be swerving around like that. And it's just going to rotate all the way around. Okay? So it's a bit like if this red line represented the rectangle, it's a bit like this. Is that alright? If the red line was to represent the rectangle. Now, what similarities does IP have to IC? There's IC, there's IP. What's their similarities? They're both perpendicular to the plane. So they're both perpendicular to the plane. So if I was to draw a little 3D image, I always do a parallelogram to denote a 3D image of a rectangle. One of them's going through the center, causing it to spin that way. The other one is going through it at the end, causing it to spin, or the full thing to spin around. Okay? So, with that in mind, they're parallel to each other. We can use the parallel axis theorem. Is IC going through the center of gravity of that object? Is the purple one in the center of gravity? Yes, it is. So I'm allowed to use the parallel axis theorem then. So IP equals IC plus MD squared. IP equals, what did I say IC was? 5/3 ml squared. What's the d distance, the distance between the two of them? 2l plus m times 2l squared. Put that into the calculator. You get a 17 over 3 ml squared. Okay, so these are the simpler versions. Now we're going to go to some composite bodies, I think. Something like this. A composite body. Okay, so you have a CD at the end of a rod. Find the moment of inertia of each of the following compound bodies about an axis through the point marked X, perpendicular to the plane of the body. So, if I was to, I wonder if I'll get away with this. If I was to do that, okay, and I can only rotate it around the center axis, but what's realistically happening is it's rotating like this, and that's point X. Is that okay? So it's rotating like that, except there's a cylinder thing at the end. A disc at the end. Okay. So what we're going to do next is we're going to work on each. We have to find the system's total inertia. We're going to break it up into two parts. We're going to break it up into a rod. The rod is rotated at the end of the rod. So you say rod IX, its inertia about the point X of the rod only. That's what that stands for. What do we know that as? 4 over 3 ml squared. Reason? The rod's mass is m, its length is 2l. It matches the generic formula. There's no need for any modifications. Good with that? Okay. Now that we've cleared the rod up, what we're next going to do is we're going to do the disc. Okay? So, circle that up. Now we're on to the disc. We'll start the disc around its center. What is the moment of inertia of a disc going through its center? Anybody tell me? Half ml squared. So we're just going to go disc on its own. It's a half mr squared. It's one of the first terms. It's in page 53. Okay, if it's radius r, it's a half mr squared. If it's radius l, it's a half ml squared. Okay, and let's call this axis C. Okay, so that's the disc around axis C. We don't want it around axis C. Where do we want it? Around axis X. What do X and C have in common with each other? What does axis X have in common with axis C? Anybody? Any takers? They're parallel. If I was to draw a slightly an image of this, like so, from a sort of a side view angle, both axes, if you look at X, X would be going down this way, if I can get it to go dead straight, and C will be going down this way here. So that point there would represent X, that point there would represent C. They're both going they're both going in the same direction. Therefore, a parallel axis theorem is accessible. And what we're going to say is the distance between the two of them? 3L, isn't it? So 3L in the difference. So we're next going to say is that, sort of ran out of space here. I'm going to say disc IX is IC plus MD squared. Now, we're talking about the mass of the disc. Not the mass of the rod is not inclusive, because you're talking about how far is the disc away from the axis X. So what we're saying is it's a half ml squared plus m times 3l to be squared. The disc's inertia about X is going to be, I didn't actually do it separately, it's 9 ml squared plus a half. Is that going to be, what's 9 ml squared plus a half, guys? 19 over 2 ml squared, yeah? Now, how do I get I total around X? Total IX. Total inertia around X. What do I need to do then? Add them together. 19 over 2 plus 4 over 3. Any takers? Sorry? 65 over 6, so you go for, okay? That's not right, is it? Sorry? Oh, is it? ML squared. Are we cool with that? Try another one. I'll try another composite. Actually, wait a minute. One that has a weight at the end. I'll leave the normal rectangular lamina alone because that's similar to what we've done already. I'll try this one here, the disc on top here. Okay, just get it on its own though. Once again, I'm aiming for IX. Okay, so let's begin. IX is all the way over here. Okay, I'm going to start with the disc. Disc. I'm first going to get the disc IC. Its IC is what, guys? Half mr squared. It's a generic disc of diameter 2r, or radius r, and mass m. So it's undergoing the usual formula. Okay. Next thing I'm going to do is go and try and change the disc to rotate around x. What's the adjustment I need to make? IC plus md squared, which is a half mr squared. What's the mass of the disc? What's its distance away from x? Its center of gravity's distance away from x. Or 3 over 2 mr squared. Okay, we're next going to go for this point mass. Okay, so we're talking about this point mass. We need I of mass. Once again, that's in your notes. Any mass is mr squared. The mass of the object you're talking about multiplied by its distance away from the axis x. So it's just going to be plus mr squared. Then your total IX is going to be your 3 over 2 mr squared plus your mr squared, which will give me, oh wait a second, mistake there. It's not r away, it's 2r away. It's from here to here. So it's a distance 2r away, not a distance r away. So be careful. So that's 4 mr squared. So it's 3 over 2 mr squared plus 4 mr squared. And what we're going to get there is, where do I have it? 11 over 2 mr squared. Happy enough with that? Okay. Party. Now, guys, what we have here is a disc with a rod with a point mass. And to add a bit of flavour in, they're changing up their numbers a wee bit. So we're really starting to feel the pressure now, okay? So, guys, IX. Are you ready, guys? IX is this. IX is it's from the we're under subcategory of rods, okay? IX of rods. If it's of length 2L, it's 4 over 3 ml squared, and that is when its mass m. We're not using L anymore, we're using R. The length is the same, so that's still 4/3 R squared, but what's different is the mass. So we're going to have to put in 6m here, and what we're going to get is 8 mr squared. Okay, that's the rod done. We're next going to move on to the point mass because it's easy marks. What's the formula for a point mass? Inertia of a point mass? Normally, it's md squared, where d is its distance away from the axis, or mr squared, where d is its distance away from the axis, m is its mass. What's its mass this time? It's m. How far away is it from the axis? 4r. It's like playing tennis, except you put the whole weight of the racket right at the top of the racket. It's going to make that racket a hell of a lot harder to swing. While if you put all your weight at the butt of the rackets where the spinning axis is, you won't notice it. You know, as top tennis players, sometimes they put a lot of weight on the bottom of the racket to adjust the balance. Some other players place lead weights on top of the racket, so the racket creates more force when you hit the ball. They do this with lead tape, okay? It's for anybody who plays tennis. Now, 16 mr squared. Is that right, guys? 16 mr squared. Finally, we're on to the disc. Anybody tell me what we're going to do with the disc? Is there any axis on the disc that could be parallel to X? The center, is it going into the board or is it lying along the plane of the board? It's going into the board. If you're worried about that, check the language of question 3. You'll see that it says perpendicular. So it's going into the board and the disc is spinning around it. So we'll get IC of the disc. IC of the disc would usually be a half mr squared. It's still a half r squared because those dimensions are the same with the generic formula. But what's not the same is the 2m. So this time it's mr squared. That's around axis C, not axis X. So then we have to go looking for axis X, and we use the parallel axis theorem. IC is mr squared. How far are we away from the axis X? How far is our center of gravity of our disk away from the axis X? 3r. No bother there. What's our mass of our disk? 2m. So it's going to be 2m or 3r squared. Add them together, that's a bit that's what's that? 18 mr squared plus mr squared gives me a 19 mr squared. Finally, total is my disk combined with my point mass combined with my rod. 8 plus 16 gives me 24. 24 plus 19? How much? 43 ml squared. Okay.